And it's kind of like what Rato said, this 3D trig is quite a lot of marks. This is 11 marks, which is quite substantial for 2D trig. But nonetheless, I did quite like the question. So usually, and I know this is such a silly thing and it's really like not important in the greater scheme of things. It says B, C, and D lie on the same horizontal plane. Usually when we ask you 3D trig questions, we do shade in like where the ground is, for lack of a better descriptor. So that's why there's a squiggle there. It's just, it helps me visualize what's happening. So first question, so that's show that sine y equals 2 sine x. There's a couple of things that we need to think about when we come to 2D trig. So I always say, look at what you're trying to prove, or what you're trying to show, and think back to how you can get that. So because of the fact that I've got 2 sines here, I'm probably going to have to use the sine rule. So that's where I went immediately. And I was initially stumped with this just because I didn't read the question. It told us that BD is equal to 2CD. So because CD was B, that therefore meant that BD was 2B. So I did actually have those 2 lengths, and that's great because those are the 2 lengths opposite the 2 angles I'm wanting to work with, X and Y. So I just set up my sine rule and I solve from there. The only thing I will just say that might trip you a little bit is I've got B times sine Y and 2B times sine X. Those B's are the same. So we can not ignore them, but because the values are the same and they will be equal to each other, we can just say sine Y is equal to 2 sine X. Okay, so I'll be honest, I was only stumped with this question because I didn't read the question or read the information. Right, 7.2, we then had to prove that whole thing. And these questions I love, but I also understand why some of you hate them. And again, my advice is go back to what it is you're trying to prove. So I always look at what are the factors I have. So I've got a B, which could come from the 2B, but likely is coming from the B side, CD. I have a tan theta, which means I'm going to have to at some point work in this right angle triangle, ABC. And I have cos X plus Y. So this kind of tells me a few things, the cos X plus Y. A, there are no signs in what I'm trying to prove, so I'm probably not going to use the sine rule. B, the X plus Y, I need to figure out an angle that contains X plus Y, and this would be angle D. So in this triangle BCD, angle D would be 180 minus X plus Y. Hence, I can get that angle that I'm working with. And like I say, because of the cos there, I'm going to probably have to use the cos rule. All right. Now, when in doubt with these types of questions, if you really don't know what you're doing, the common side, so this side BC, is probably going to be important. If we just think about this in terms of us wanting AB, AB is in the right angle triangle. So here it is. It's the side opposite theta. And so, yes, we could use sine, we could use tan, but if you think about it logically, we're able to get BC by working in the bottom triangle. Oh, sorry. So tan theta is equal to opposite, which is AB, over BC. And so if we want AB, that means we need BC times tan theta. And there's the tan theta that I want in my expression. So I kind of just like break down for myself exactly what it is that I want and how I'm going to get there. So I know I need the length of BC, so that's what I'm doing here. And because of the cos, I'm using the cos rule. Obviously separate words, but you know what I mean. So I'm using the cos rule. Just substitute in, get all of that. And then once you actually have BC in terms of the X, Y, and B, you can see that you now have using my mind. You now have part of the expression. So we've got the B, we've got the 5 plus 4 cos X plus Y. So we've got the B and we've got the 5 plus 4 cos X plus Y square rooted. So the only thing now we need is the tan. And as we can see, once we substitute in BC, we then have it times tan theta. So always go back to what it is that you're trying to prove in order to figure out your methodology. This was a really nice one because we don't actually often use cos rule. We often use sine rule. So this was a really nice example. And then just 7.3, this is just a substitution question. So I haven't written it out. You just quite literally, so they want the height of the tower. So they want the height of AB, which you now have an expression for. if b equals whatever. So all you do is you take all of these values, and even if you couldn't do 7.2, you substitute them into that expression, and that's 2 marks easily. All right, so that was the first one. I'll wait in case you want to screenshot all of this. The second one was a nice trig graph question. And like I say, 5.5, I'm still muddling over because I hate K questions and functions. It'll come to me, I just don't like them. All right, question 6. So you were given a tan function, tan bx, and a cos function, cos x minus 30. And we were told that P91 lies on F. Right. So a couple of things, whenever you get functions, and it's algebraic or trig functions, really makes no difference. We should do this. Analyze what you have. So this tan bx, the bx means there's a period change, and this cos x minus 30 means 30 degrees to the right, just to understand what's happening. And this is where your knowledge of your parent functions is so important. The point P91, okay, so that information there. What we need to remember of a tan graph, I'm not going to draw the whole thing, is that a basic tan graph, so just tan of x, has a coordinate at 45 degrees 1. Depending on where this coordinate shifts to or moves to, it tells us either information about our period or about our amplitude. So if it's no longer at 1, let's say it was at 2 or 3 or something, that indicates to me that the amplitude has increased, or if it was a half, has decreased. If it shifts left or right, so like this one has, where it's now at 91, this implies a period change. So rather than it being 45, it's stretched out to 90. Now that's double, okay? And so that means in 6.1, where it asks for the value of b, I know that my value is a half because my period is being stretched. It's no longer at 180, it's now at 360. I also know this because asymptotes of a tan graph usually exist at 90 degrees. I can't have an asymptote at 90 degrees because I've got graph. It's happening 2 times later. It's been stretched out. So that's how I also know that my b value is a half. Right, write down the period of g. So that's your cos graph. Nothing's changed in terms of the period, so it's still 360. Write down the coordinates of a, the turning point of g. So normally a cos graph, looks something like that. Terrible cos graph, but you get what I'm trying to say, hopefully. So without any shifts or anything. And this point over here would usually be at 0, 1. However, because your cos graph is now moving 30 degrees to the right, this must move now to 31. It's still at a maximum. I haven't shifted it up or down or changed the period. But now instead of being at 0, 1, it's now at 31. And again, knowing your parent function makes that super easy. Right, 6.4, write down the equations of the asymptote of tan b x plus 20. So all you're doing is you're taking this original tan graph that I gave you and you're shifting it 20 degrees to the left. So all that means is that this asymptote at 180 must shift 20 degrees left, so at 160. This asymptote at negative 180 must shift 20 degrees to the left, so negative 200. But it does say only in the interval given, so that's why I've only got one solution, because that negative 200 is outside my interval. Right, and then 6.5 says, determine the range of h if h of x equals 2 times g of x minus 1. I always just work out the new equation. So you times the cos graph by 2, so you change the amplitude, and then you shift it down 1. So I do see the question on the chat, I'll get to you now. The amplitude change means that it's now obviously at a maximum of 2 and a minimum of negative 2. And the shift 1 unit down means this now goes down to negative 3, and this maximum goes down to positive 1. And so that's how I know my range is that. So it's understanding the manipulations that you are performing and then being able to go from there. A 6.1, why is it a half, not 2? Okay, so period changes work. I don't know where I was going with that statement, sorry. So a half stretches it out. If it had been tan 2x, it means everything is happening twice as early. So this 45 degree point would now be at 22.5. It's happening twice as early. The asymptote that's usually at 90 would now be at 45, twice as early. But because it's stretching out, my B value or my period has to be greater. So it becomes a half. If you think of how you work out period, it is, this will come to me eventually, it's like my brain. It's your new period divided by your old period. Your new period is now at 360 degrees, whereas your old period, I've obviously mixed this up here. Old minus new, old divided by new, sorry. And so you would have 180 over 360, which is a half. Sorry, man. It's clearly been a while. But essentially, it's because of the fact that it's stretching out. Just write this properly. Oh, and then I'm going to write the same thing. Old divided by new. That says new. Okay. Right, so if you want to screenshot that, like I say, 5.5, I'll show you where I'm at. It's not very far, but it's getting me, and I will get it. I just need to think about it. All right, so 5.5, just for those of you, it says for which values of k will sine 2x plus 30 plus k equals 3 have no solution. So what I've done is I know that k and 3 are both constants, so it implies a shift up or down. So I've grouped them together. And then I've just analyzed the 2x means a period change. It's squished. And the plus 30 means 30 degrees to the left. This is me just trying to sketch all of this stuff. But the problem is that, so this is the graph of, it would be more like that. This is the graph of sine 2x plus 30. If I now do the shift down minus 3, I end up there. And currently it already has no solution. So that's why the question is stumping me, because why ask for no solution if it already has no solution? It's not cutting the x-axis. So I just need to think about it for a second. I'll get back to you. Do you remember what paper this was from out of interest? If you don't, it's not the end of the world. Oh, okay, so this year. Yeah. So let me just think about this. I'll get back to you. I might have to post it on the Google Classroom. I feel like I've just done something stupid. I just need to figure out what it was. I just haven't. So I will let you know. But hopefully the rest, that's all good. And like I say, I will come up with an answer to this and I will put it on the Classroom. All right, guys. Right. Let's have a look. So Euclidean geometry. I'm not going to go into detail into all of these things, just in terms of like theorems and stuff, because this is stuff that you know. What I am going to say though is, excuse me, on the Google Classroom, I have uploaded a while ago now, but it is there, all of the written out circle proofs, because you are going to be tested on a proof. You just need to accept that. So that is all there for you. And then in the like info packs, all of the theorems are outlined for you there as well. All right. So Euclidean geometry, these are sort of the bits of information that we currently sit with at the end of grade 11. So let's just do this. Right. So these theorems, the straight line, triangle, and the circle theorems, you have in your sort of arsenal at the end of grade 11. By the end of grade 11, you've finished all of your circle theorems. And obviously, straight lines and triangles you've been doing since grade 8. Just a quick reminder in terms of proving. Anytime you want to prove something, you're using a converse. So if you want to prove a cyclic quad, you use all of the converse reasons. If you want to prove a tangent, you use the converse reasons. If you want to prove parallel lines, you show that certain angles are either equal or supplementary. And I've broken all of this down for you here. Right, so circle theorems, really important to know. Triangle, straight line, parallel theorems, also all really, really important to know. Like I said, this is all on Classroom, but I will wait in case you want to screenshot any of it. And like I say, this is just knowledge you already have. There's nothing new here. Okay. And then in terms of your triangles, and we'll make this bigger and then I'll shove over. We learn the proportion theorem and essentially similarity theorem in grade 12. So these are your, well, this is your proportion theorem. Again, the proof is in the pack. If it isn't, obviously just let me know, but you should all have the proof in any case. So that's your proportion theorem. There is also the midpoint theorem that you learned in grade 10, which is the converse of this theorem, and talks about a line dividing your triangle in proportion. Prop theorem and similarity are tested together a lot of the time, and it is generally the complex problem solving question, just how it works out, unfortunately. So you have the proportion theorem. I'm just waiting here in case anyone's still wanting to screenshot. And then the similarity theorem. I don't actually know how many teachers do the similarity theorem like as a proof. I'm going to be honest. It's not a hard proof at all, like at all. And like I say, it is all on the classroom. And if it isn't, just let me know if for whatever reason I've done something silly and forgotten it. But it is all there. So just bear in mind that you do need to know these proofs. There are 7 proofs that you need to know. If you go to these exam guidelines that I always harp on about, so yeah, if you take that QR code, it tells you in the exam guidelines exactly which theorems you have to know how to prove for Euclidean geometry. It tells you everything for each section, but it does tell you which theorems. And just to like give you a idea here, last year's grade 12s were asked the theorem proof of this first theorem that you learn in grade 10. Like literally this very first theorem that you learn in grade 10, that was the proof question they were asked in their finals last year, which a little bit mean if I'm, being honest, but just be prepared for the fact that we can ask you any of them. All right. So that was your similarity theorem, just in case you're still wanting to screenshot. Okay. And then the last little bit I have here is just a reminder, because this comes up a lot in similarity and proportion, just a reminder about your area ratios. Okay, so area ratios, we often, like I say, like a lot of the questions are prove that or write down the ratio of area triangle whatever to area triangle whatever. And there's sort of 2 situations you need to be mindful of. First situation is when your triangles have the same perpendicular height. So they come or have a common common vertex and then the same perpendicular height. We are going to use then the area rule of half base times height. Reason being, the height is common. And so when you eventually go and substitute in, all of those heights will cancel and then you're just left with a ratio. And what you should see is that the ratio of your areas is a ratio of the base lengths. And you could just learn that and use that. But obviously there will be some working out, but just something to bear in mind. And then the other type of scenario that we can give you is where you have these parallel lines where you create this common angle. So angle A at the top, there's a common angle between both triangles. If you think back to like similarity from grade 8, grade 9, we often gave you questions like this where we said, prove that this APQ triangle is similar to ABC. And you'd always say angle A is equal to angle A, common angle. When it's a common angle situation, this is when we use our trig rule. So area equals half AB times sine C. And again, the reason is sine C will be common. So you'll be able to cancel out the angles and obviously the halves. And then what you are left with is your ratio that you want. Again, you can remember it as ratio of your corresponding side squared. But like you're filling in a ratio. So I don't think that's super important to know. But just bear in mind that when we do ask you these area ratios, there's two ways to do it. Either with a half base times height, if your height is common, or with the sine or the area rule from trig, where your angle is common. And it just allows you to simplify things easily. All right. And then this is just a random sort of little statement. It has to do with the parallel line situation. You can do with that what you want. But these two, the two type area ratio things, that is very useful to you. Okay, I'm just waiting in case you do want to screenshot any of that information. Like I said, particularly this type 1, type 2 thing. Okay. Right, so in terms of the questions that you can expect, I know I'm going through this, but guys, this is very much just like content. Like you have to just know the theorems. You have to understand how to apply them. And obviously, practice makes perfect. So what can you expect for these questions? You're going to get a theorem proof. Accept it now. I'm not saying that we won't ask you a proof of similarity and proportion. It's just not one that often comes up. Ooh, excuse me. But like never say never. Maybe you are the So know your proofs. And like I say, in the exam guidelines, which is online, it does tell you exactly which proofs you need to know. You then sort of get led into geometry nice and easy with a just basic numerical question, which we're going to have a look at in a second, whereby we give you a relatively straightforward diagram. So like you won't have two circles, let's say, for example. It's a circle, maybe a couple chords and lines and stuff, but relatively straightforward. We then give you known angles. So this angle is 74 degrees and this one is 15 degrees or whatever. And then we ask you, find the size of angle A2, Z1, whatever the case is. So it's just a basic question. And what you should bear in mind at this point is that we're testing your fundamental knowledge of the theorems. Can you identify the theorem within a diagram? And can you then use that to find an unknown angle? We then need you into a slightly more complex question with some algebraic. It's basically exactly the same as the numerical, except for the fact that instead of me now saying this angle is 74, I'm going to say, let this angle equal x. This is often the question where we say, write down 3 other angles, all equal to x with reason sort of thing. And often we then, like I say, like increase the complexity by then saying, prove that, I don't know, angle O2 is equal to a quarter of angle S or something like that. We kind of introduce the idea of showing that things are equal, proving that something is something. And this kind of then combines the next point where you have to prove things. Tangents, cyclic quads, or parallel lines. It'll generally be one of those unless it's like a problem-solving question. So, I don't know, like prove it as a rhombus or something. That typically is an analytical question, but you're going to use geometry or geometric reasons to get there. And then you have a similarity proportion question. And generally, this does combine all of the concepts. So like straight lines, circles, similarity, proportion. The similarity and proportion is often within a circle question. So a combination of. And so in my opinion, you should all be able to do these first 3 types of questions. The proving is a little trickier, but again, you should all be able to do it because you have all your converse proofs. I personally just don't enjoy similarity and proportion. It's not a theorem I particularly like. So for me, I would consider this for myself a more complex problem-solving question. And then obviously the combination questions or similarity and proportion generally harder. So we should all be able to do the first, I'm going to say, 25 marks of Euclidean geometry, which is already over 50% of the geometry. So if we can do the basics and if we can apply our theorems appropriately, we should be absolutely fine. Okay, let us though have a look at some questions. Obviously, if you guys have questions at any point, please ask. I feel like I'm talking a lot, but also just because I'm giving you a lot of information at the moment. But please do ask if you do have any questions. All right. Okay, so this was June paper 2 this year, if I remember correctly, in Mpumalanga. I thought the questions were really nice, particularly for the geometry. So this is, so 8.1 would have been the theorem proof. I'm not doing any theorems with you. You must learn them. It's one of those questions where either you bank those 5-6 marks or you lose those 5-6 marks. Obviously, my opinion is bank those 5-6 marks, but it's up to you at the end of the day. All right, so this is then, it's a theorem proof question, and then we lead you in with a nice, easy, basic question. So it says, in the diagram below, O is the center of the circle with FE equal AB and BO parallel to CD. Angle O2 is equal to 88 and D2 equals 23. Tangent PAS touches the circle at A. Right, so I don't know how many of you remember when we did Euclidean geometry, I spoke about Dr. CPT. Right, the Dr. CPT essentially highlights for us 5 incredibly important characteristics that we often use in circles. So D is diameter. If you can identify a diameter, do so, because it means that you might have angles in a semicircle. You might be able to identify radii. You might be able to identify the center of your circle and potentially use angled center equals 2 times angled circumference. So if we can identify a diameter, that's great. R, radii for very much similar reasons. C, if you have any cyclic quads. P, your parallel lines. And T, your tangents. So if you can identify any or some of these characteristics on your diagram, it's just going to help you guide your mind in terms of the theorems that would be appropriate for you to use here. Right, now, if you want to highlight all of this as you go along, that's fine. Particularly with the cyclic quads, it can be a bit much. So you make your choice at the end of the day. So I'm going to go through here. I know that O is the center of my circle, which means that AD, or AOD rather, as well as COD are both diameters. Okay, I then do have a few radii going on here. Obviously, OF, OD, OC, as well as OA. Those are all diameters, as well as OB, diameters, radii. Right, there are going to be a few cyclic quads, so, you know, bear in mind, just bear with me kind of thing. And as I'm saying that there's going to be a few cyclic quads, can't identify a single cyclic quad for myself. I had so many words in my head, and now they're all just gone. Right, so a cyclic quad could potentially be like A, F, E, B sort of situation. Those are all 4 vertices on my circumference. Just because we don't have chords or lines there joining doesn't necessarily mean that they aren't. So I'm not going to draw in the cyclic quads. I find it a bit confusing, but just bear in mind your cyclic quads. If you want to join them in, if you want to draw them, absolutely go for it. Parallel lines, I did see the question on the chat, so don't stress, I'll get to you now. Parallel lines, obviously we were given 2, so that's awesome. OB or BO parallel to CD. And then we were also given a tangential line or a tangent line, PAS or SAP, whatever you want to go with. So those are all the characteristics that I can identify in terms of Dr. CPT. And then also just bear in mind, we were told that FE is equal to AB. So it is on the diagram, so you don't need to stress. Those 2 lengths are equal. All right, let me just have a look. Can you know, if we know that, or if we know where the center is, sorry guys, Kanye's question was, they don't have to say in the given information that there's a diameter. No. If you know where the center of your circle is and you have a line going through the center of your circle from one end of your circumference to the other, it's a diameter. Usually, though, if we want you to use that information, we will say COF is a diameter, but yes, if you can see your line going straight through, then it is. Lorato DCBE. Yeah, that's also a cyclic quad. AD BCD is a cyclic quad. FEDC is a cyclic quad. There are lots of cyclic quads that we have here, which is why I often don't like drawing in my cyclic quads, just because it can get a bit overwhelming. I just keep in mind that I do potentially have cyclic quads. All right, so 8.2.1 asks us for the angle of O3. So this is a 2 marker. I'm going to give you guys 2 minutes to think about it. We want O3, which is this angle over here. So think about it, O3 with a reason. Nice, Muflatsi. Can you give me a reason for why? Lovely. Okay, awesome. So O3 is equal to 46 degrees because angle at center equals 2 times angle at circumference. I will obviously show you this all now. So 46 degrees, angle at center. I hate this reason. Circumference. Just also a very random statement, sorry. In that assessment guideline, exam guidelines thing that I mentioned earlier, it does also, if you struggle with reasons, it's like, I don't know, like page 5, page 6. Anyways, it's in there. There are like 3 pages just of accepted geometry reasons. So if you do struggle with your reasons, go and have a look at that, because it tells you exactly which reasons you can use, and if it's not on that list, don't use the reason. Right, so there it is. In these types of questions, particularly the more basic questions, you get a mark for the answer and a mark for your reason, hence 2 marks. All right, if you struggle with angle at center, angle at circumference, what you need to remember is that they need to come from essentially the same arc or the same chord. So if you have a look here, chord BC subtends an angle at your center, O3, but the same chord also subtends an angle at your circumference. Please note, grade 12s, this is not angles in same seg. Angles in same seg, all 4 vertices must be on the circumference. This is angle at center because you've got one angle at the center, subtended from the chord BC, and the same chord BC also subtends an angle at the circumference. So please, please just be careful when you do go and have a look at that. We don't want to make any silly mistakes. Right, so I like to fill things in on my diagram as I go along. Paper 2, you get an answer book, and so you are able to scribble, highlight, do whatever you want to do in your answer book, which is really nice, especially with the geometry and the analytical geometry. Kani?
Hi, ma'am. Can you please explain that white segment thing? Like, because I always get them confused. Like, why is it not?
Okay, sure. So I'm just going to draw 2 little diagrams here because I think it'll be easier to see like that. So angle at center. And then we have angles in same seg. So angle at center, you need to know where the center of your circle is. And essentially what's going to happen is that a common chord will subtend 2 angles. So when I say common chord, this chord or segment, actually, it doesn't really matter. That segment of my circle subtends an angle both at the center and the circumference. So I always think of it, if I took my fingers and I went from the same points, can I get an angle at the center? Can I get an angle at the circumference? So that's what that says. Now, bear in mind, there's lots of variations from this. I could draw something like that. That's still, because it's from a common chord, angle at center equals 2 times angle at circumference. We also have a situation whereby we can have the reflex angle. Let's actually draw this in a different color. I can be working with the reflex angle. So if I have sort of a quadrilateral looking thing, which that clearly does not look like one, this reflex angle will then be double the angle at the circumference. It's still an angle at the center. It's still an angle at the circumference. We're now just talking about a reflex angle. So that's your angle, center, angle, circumference. And really the most important thing to kind of differentiate the two is the fact that one will be at the center, one will be at the circumference. When it comes to angles in the same seg, all right, this is where we have like a bow tie butterfly looking situation. And what's really important here is that all of your vertices have to be on the circumference. Okay, angles in the same seg is a cyclic quad reason. So all four vertices of a cyclic quad must be on the circumference. So this technically is a cyclic quadrilateral. All right, that's what angles in same seg is. And so if you now go once again from a common chord or a common segment of your circle, so let's say, for example, we go this one over here, we then know that the angles subtended from that common arc or common segment is exactly the same. If we went the other side of our circle and we looked at the segment of our circle that's in purple here, the angles that they subtend or it subtends on the circumference are then equal. So those two angles are then equal. But the key thing here is that all four vertices must be on the circumference. Does that make a bit more sense? Awesome. Right, I see some of you are already doing question 822, which is awesome. I just want to say here, guys, the second you have 3 marks in the beginning questions, it generally means that you have to do some working out before you actually get to your answer. Okay, so oh, sorry, it would help if I knew what I was doing. Right, so the question says, calculate the size of angle D1, which is this one over here. I'm just trying to figure out what some of you are doing right now. Okay, so Mtlati, why have you said 180 minus 88 and then divided by 2?
Hello, ma'am.
Hi.
Like, it's a triangle OCD, which forms 180. And then, like, OC is equal to OD, which means base angles of a triangle, which means CD is the base angle. So, which means, like, 180 minus 88 divided by 2 is angle C and D. And then you take angle D2, you subtract to give you angle D1. But then, like, there's also the approach of the others, the straight line, and then it forms angles at center. Like, so I just used that one.
Oh, didn't even see that angle at center one. Nice. Okay, cool. No, that's awesome. Sorry, I'm also now following. Thank you. All right, so guys, I will go through all of that. Well done on that angle center thing. Like I said, did not see that at all. Would not have seen it unless you pointed it out. All right, so guys, D1, there's actually a few ways that you can do this question. I can't remember what I did, but don't know why it took me so long to figure this out. So we know that OC is equal to OD because they are both radii. That's not how you spell radii, is it? Let's try that again. So that is equal to that radii, which means that exactly as Mtlati said, OCD is equal to ODC. OCD is equal to ODC. Angles up equal sides. And so, yes, we can absolutely say 180 minus the 88 divided by 2 to get what these angles each would be, which are 46 and 46. And then you can go ahead and say sum of angles in a triangle. So D1 would be equal to 23 degrees, some angle in triangle. Okay, that's absolutely fine. Nothing wrong with that. Matlatsi's also pointed out another reason, which actually probably would have been a bit more straightforward if we just think about it. But like I said, never in a million years would I have seen it, or at least would have taken me much longer. So option 2 is that you could have used angles on a straight line to work out what 04 was, which would give you 46. And then using this whole logic that we've just said, you've got a common chord AB. It creates an angle at the center. And the same chord AB also creates an angle at the circumference at D1. And so you know it's 23 degrees. You could have used angles at center equals 2 times angle at circumference. Like I say, I did not see that. But you absolutely could have used it as well. So you would have done angles on a straight line, got an 04, and then used angle at center. Right, and again, guys, obviously, if at any point you have questions, please just ask. I know that geometry can be confusing. Alrighty, then we have A1. So A1 is, where's A1? Oh, there it is. Okay, obviously I've now done that. So A1 is this bad boy over here. Have a think. Let me know what you think A1 size is. And also take note of where your angles are. A1 is right by a tangent. It's literally an angle created between the tangent and a chord. So we should be thinking about the theorems that maybe apply. Matlatsi?
Ma'am, I agree. Angle AD is a diameter, right? So does
Say
that
that
mean
again, sorry?
line AD is a diameter, right? So does that since forming angle B, does that mean that B is 90 degrees or?
So like I said, I can't remember who said it. Technically, we should say AOD is a straight line and COF is a straight line. So where possible, avoid it. But yeah, what were you thinking?
I don't know.
Well, let's see. We could actually probably prove it. So OB and OD are radii, which means B1 is 23. If O4 is 46, and again, radii, OB and OA, we can use sum of angles in a triangle.
Because, ma'am, like, I get it that tan chord, like, shouldn't the tan chord, I don't know, right? Thank you, ma'am.
Yes, you're on the right track, though. So, yes, it is 90 degrees. Okay, so exactly as Kani said, you're on the right track. We've got an angle created between our tangent, PAS, the chord AB, and we know that that is equal to the angle in the opposite segment. And so what that means is that according to tan chord theorem, A1 is also equal to 23 degrees. Arato, PS perpendicular to A. Okay, so again, let's not assume diameters. I mean, like, they're straight lines, and I have actually proven that there are diameters, but yes, you could say that PAS is perpendicular to OA, tan perp rad. That's fine. Right, so A1, 23, tan chord theorem. Right, we then want C1. I feel like my diagram's becoming a bit overwhelming, but we move. So here's C1. What is the size of C1? Right, Miss Lexi, I like what you are thinking and you are on the right track, but just remember, it would be the whole angle at C. So that whole thing would be 46 degrees. So be careful. Honey?
Wouldn't it equal 23? Because equal chords, I don't know if it's right. Equal chords obtained, like, equal chords produce equal angles.
Perfect. Perfect. So guys, this is one of the corollaries that we often forget. Sorry, I can't say the word, so we'll just pretend I can. When you have equal chords, so FE is equal to AB, the angles that they create at the circumference, so in this case, D1 and C1 are equal to each other. So because we know D1 is equal to 23, we automatically know that C1 is equal to 23. Now, once again, there are other ways that you can go and do this. Because we know D1 and D2 are 23 degrees, we can't assume that this line CE bisects, but because we have, we don't actually have enough information. We don't actually have enough information. Sorry, I was getting myself sidetracked. We would actually have to use our equal chords, equal angle situation. So I'm going to say it again. When you have equal chords and they create angles on the circumference, the angles opposite those equal chords are equal. And so C1 is equal to 23, equal chords, equal angles. And it is, I'll come back there now. In the information I gave you earlier, there it is. So two equal chords, the angles they create on the circumference are then equal to each other. Kani?
Never mind, ma'am. It's fine.
Okay. Right, and then the last one that we need to find, guys, is angle C2. So we've just worked out C1 is 23. Most of you probably have C2 in any case. There are a couple different ways you can do it. So either you can work in triangle OCD and say the angles are equal sides. So you know OCD equals 46. Apparently 460, 46. Or just bear in mind, you do actually have parallel lines. So if you look at your parallel lines, it creates a zigzag. And so this angle is equal to that angle of 46 that we found earlier. And because we then know that C1 is equal to 23, we can just subtract the two. So I used alt angles when I initially did this. All right. So like I say, these first questions, often straightforward questions testing your ability to apply your theorems. This is going to sound like, again, such a random statement. And obviously, I know this is not for everyone. I don't know where my bag is. I had a bag at some point. So as you can see, my diagram is quite a lot. Obviously, technology, I have the luxury of just erasing what I don't want. But maybe, especially if you do like the colors, but it gets a bit overwhelming, use a pencil. I know a lot of you also use those like erasable pens, use those. You do get erasable highlighters, use those, but kind of use something where if it does get overwhelming for you, you can just take it off. All right. So I wish I had my bag. I have like a whole set of erasable highlighters that I use for geometry, just because I know that I like to visually see what I'm doing, but I also like this is really too overwhelming for my brain. I can't do anything productive with that. So just find things that work for you as you go along. All right, I'm gonna wait here for screenshot, and then you're gonna try the next one by yourselves. All right. Okay, so the next one is algebra type 1. I just want you to try 9.1. Okay, so the 3 other angles equal to x. That's a lot of e's. 3 other angles equal to x. But let's just read the information. So it says in the diagram below, TWSK lies on the circumference of the circle, which means that is a cyclic quad, such that TW is parallel to SK with O as the center of your circle. K1 is equal to X. All right, so take a second, have a think. I know it says 4 marks, but I will give you 5-6 minutes to give this a try, just so that you can have a look at the diagrams first. And like it says, I want 3 other angles equal to X. And obviously, guys, if you've got questions, just ask. Matlatsi, I'm not 100% sure on the T1 alt angles thing, unless it's just a typo.
Oh, sorry, ma'am. I meant T3.
Yeah, okay, thought so. Right, double check the S2. So S2 isn't really like an alt angle situation just because of the fact that that line doesn't carry on to make the zigzag sort of thing. It just sort of stops at the center. So just be careful. You're in the right area. I'll give you guys 1 more minute and then we'll have a look. If you want to go ahead and prove that SOFT is a cyclic quad, awesome. Okay, so it would be angle S. Just be careful. We would have to say WSK. So we'd have to use the actual labels because there are a few angles. There are a few angles at S. So just, yeah. All right, guys, very nice. So Mthlasi's given some answers here. I'm hoping we're all on the same track, but I'll go through it here. Right, so first one that was mentioned, nice, Kani, weird, nice. Nice, guys, well done. All right, so it doesn't really matter where you start, you do you. T3 is alt angle. So if we follow our parallel lines and we create that zigzag, just remember it must be a continuation of your lines. That's just going to upset me. So let's try that again. So zigzag shape, those are then alt angles. So T3 equals X. You give your reason, alt angles. And remember to state your parallel line. So TW parallel to SK. Great. So this is equal to X. W1, very nice. Angles in same segment. So if we just grab another color here. Here's your bow tie butterfly shape. And so yes, W1 is angle in the same seg with K1. And then exactly, again, also angles in the same seg, but now with T3, we're going to get there then. Or you can use alt angles again. It's also up to you. So here we go. So option 1 is alt angles. So now going your zigzag the other way. You get that this angle, cool. You get that this angle WSK, that whole angle, is equal to X because alt angles. Or you can use angles in the same seg, T3 and WSK. Doesn't matter which reason you choose to use. So WSK is also equal to X, and I'm just going to use angles in same seg, but you can use alt angles as well. All right, and we've got 3 angles, each equal to X. I am going to take all of these scribbles off and just write in the X's that we have. Mtlatsi?
Then, is there a difference? Like, what is the difference between angles separated by the same chord and angles in the same segment?
Can you say the first bit again? Sorry, you cut off a little bit.
Like, what is the difference? What is the difference between angles subtended by the same chord and angles in the same segment, if there is a difference?
Okay. So it's kind of one and the same, I suppose, except you don't necessarily need a chord for angles in same seg. So if we have this situation, this is clearly an angles in same seg situation. However, if you had a chord here, this chord would be common to both. And so it would be equal in both of those triangles. So it would also be an angle, equal chord, equal angle situation. So technically it's the same thing, but we don't necessarily have to have a chord for angles in same seg. I don't know if that makes sense. Okay, great. I'm glad it made sense. T3 equals W1. So just be careful. We can't say that because F isn't the center. O is the center. So just be very, very careful. We can now say that TF is equal to FW because we have those equal angles, but we can't use it as a reason. We don't know that those sides are equal, sorry. So Kanye, I hope that makes sense. Awesome. Okay. Right, so guys, 9.2. So like I said, often in the algebraic question, it is this name 3 angles, name 4 angles, name whatever angles equal to X. And then we start to introduce those proving questions. So this question is asking us, prove that SOFT is a cyclic quad. All right, so let's first identify where SOFT is. Not that. Stupid thing. Okay, SOFT. SO to F, which there isn't a line there, but I'm going to draw one anyway so that we can see it, and then to T. So this weird looking shape over here, we want to prove is a cyclic quad. Now, guys, there are 3 ways for you to prove a cyclic quad. Converse angles in same seg. So if you can prove that the angles in the same segment are equal, you can prove it's a cyclic quad. Exterior angle of cyclic quad. If you can prove the exterior angle is equal to the opposite interior angle, converse exterior angle cyclic quad, and then converse interior angle cyclic quad. So if you can prove that the 2 opposite interior angles are supplementary, they add up to 180, you've proven it's a cyclic quad. So what I like to do with these types of questions is I like to first go and see, can I identify any of those 3 converses? Sometimes there will be multiple ways to do it. Sometimes you might identify one way, but it actually ends up not being useful to you. And so just go slowly, just go carefully, just be mindful of what you're trying to do. So for me, the first thing I'm immediately seeing is that I have a bow tie in here. So I'll show you my bow tie now. Oh, golly. Right, so there's like a bow tie looking shape, which essentially tells me that if I can either prove T2 is equal to S1 or F4 is equal to O2, I've proven that the angles in the same seg are equal. And then I've proven it's a cyclic quad. I maybe could use interior angles, and I maybe could use exterior angle of a cyclic quad. I will explain to you why I don't think those are going to be my reasons. Firstly, because of this line OF. I would have to construct that line. That doesn't exist right now. The angle created between OF and then this line FK, that is the exterior angle. So I'm now like cutting up angles. It's a bit complicated. So I'm going to go with the angles in same seg situation. And I'm now going to have a look and see, is there a way for me to work out F4, O2, or even S1 and T2? Now, just having a look at what's going on here, I'm hopefully you can see that I'm obviously going to go F4, O2. If it's not obvious, that's fine. I'll tell you why. O2 is an angle at the center, all right? The chord TS subtends that angle at the center, and that same chord TS subtends the angle X at the circumference. I can easily work out what O2 is. So immediately I know that O2 is equal to 2x because angle at center, you can't use the at sign, so maybe let me not be lazy. At center equals 2 times angle at circumference. All right, so and please notice I haven't used the reason angles in same seg at any point. That's what I'm trying to prove. I'm using my other theorems that apply in order to get there. So I now know that O2 is equal to 2x. If I can get F4 to also be equal to 2x, then I'm winning. And it does, because if you have a look here at this triangle TWF, F4 is an exterior angle, which means it's equal to the sum of the two opposite interior angles. So F4 is also equal to 2x because of exterior angles of triangle. And so what that means is that I have proven that my angles in the same seg are equal, O2 and F4, because they both equal 2x. And so therefore SOFT is a cyclic quad because converse angles in same seg. Now, once again, grade 12s, because this is where we often go wrong. We cannot say that F4 is equal to 2x because of angles in same seg. We are trying to prove it is a cyclic quad. You can't use any of the cyclic quad reasons. You have to find other ways to go and prove that they're the same to then say, yes, there are angles in the same seg. And so, yes, this is a cyclic quad. All right. So kind of similar to what we did when I was explaining the 2D trig question earlier. Look to where you need to be. I know that to prove a cyclic quad, I only have 3 options. Can I identify any of those options for myself? I could identify the angles in the same seg, and so I kind of led myself with that. Right? These proving questions are not supposed to be super easy. They are the complex questions. But just always think about, what do I know I need to do, i.e. my 3 options? Can I get any of those 3? Right, so I'm just making it a bit small in case you want a screenshot. Lorato?
Ma'am, so I understand how you did you used O2 and F4. So ma'am, would it be complicated trying to prove basically that S1 is equal to T2 since they're
So the
also
reason
in the same seg?
Yeah. So the reason I haven't chosen to do those 2 is because, I mean, you might be able to get there in the end, but my problem is that I don't know what portion S1 is of this X, and I don't know what the relationship between T2 is and the rest of the angle. I just don't have enough information to get those 2. If I had more information, then maybe I could. Right now, I don't have enough information to get there. Okay. Kanye?
So I understand the working out of everything, but I don't understand like how that shows that it actually is a cyclic quad. Like, I don't know if you understand what I'm saying.
Yeah. Do you agree with me that one of the reasons in a cyclic quad is that if the angles in the same, or rather, a cyclic quad has angles in the same segment equal to each other?
Yes, ma'am.
I don't know if that made any sense. Okay, wait, let's jump up here. Right, so cyclic quads. If you have a cyclic quad, the angles in the same segment will be equal to each other. But I now want to go the other way. I'm trying to prove that something is a cyclic quad. So if I can show that the angles in the same segment are the same size, then I can go and state, okay, cool, all 4 of these vertices do actually fall on the circumference, hence cyclic quad.
Oh, okay. Thank you, ma'am.
Does that help?
Yes, ma'am.
Okay, good. All right. Loved this next question. Don't know if you'll feel the same, but you'll be fine. Lorato, I do see your hand. I'm just going to put this next question up so people can give it a try if they want. So 9.3 says, prove that ST is equal to 2SO times sine X. Problem solving question, or complex problem solving question. I would classify it as. Have a think, have a try, see what happens, see where the wind takes you. Lorato?
Ma'am, so in question 9.2, we obviously see how like there's a side that's not exactly on the circumference for the cyclic quad. So in such cases, do you have to just think about like constructing a line and basically like visualizing what they
Yeah.
trying
So
to
essentially what this, exactly. So this is saying there's a circle going through S, T, and O like that. So it's a whole new circle. Because we've proven it's a cyclic quad, we now know that there's a circle that passes through those 4 points. So we won't necessarily have anything on the circumference, but we know that the circle's there. And yeah, if there isn't a line there, you can construct it, imagine it, whatever you need to do. Right, I'm going to give you another minute or two to mull this over. I'm not saying this because I don't think you can do it. I do think you can, but just take a second or two to mull this over, and then we will chat about how we can deal with this. Again, a really nice question because it draws on your trig knowledge, which we don't always expect to come up in Euclidean geometry, but it definitely can. All right. There are 2 different ways to do this. So I came up with 2 ways. In my, I don't think there's more. Do you know where it's going with that? Yes. Kanye, if it makes you feel better, if I was you, I probably would skip this too, if I'm being honest. Like, if I think back to who I was in high school, I probably would have done the same thing. But we got this, and so we can do it. Oops. Oh, you guys are funny. I'm assuming from the comments in the chat, we're not feeling this question and we don't really want to do it. Or at least not do it by ourselves. All right, so if we have a look, so it says prove that is, so firstly, guys, if you're feeling stuck, firstly, just identify where all of these things are. Like, that is your first point of call. See where these things are, and then you can decide what you need to do. So ST is this chord over here. It then has, so it's got ST, we've got 2 SO, so SO being this radii over here. Obviously, I can't draw a straight line, so that's cool. There we go. And then it's got X. All right, now we've got lots of angles. We've got a 2X, we've got an X, we have all of these things. But what I want you to think about in your heads is the fact that ST and SO form part of a triangle. If we were to go and have a look, TO would form the third side of that triangle. I then have this angle 2X as part of my angle here. Now, 2X is obviously not what I want, but we know about double angles, and we know that double angles can be expanded to give us a single angle, for lack of a better description. All right, so I'm just going to do 9.3 over here where we've got some space. So we want to prove ST is equal to 2SO times sine of X. Right, now you can use the cos rule or you can use the sine rule here. It doesn't really matter. I went cos rule initially, but I think the sine rule is a bit easier. So I'm going to do sine rule and we'll go from there. So sine rule says to me that I need to have a pair. Now I'm looking for ST and I have its opposite angle. So that's great. So ST over sine of angle 2X is equal to. Now, because SO was the angle involved here, I'm going to go with the side SO, obviously, SO over. But now I need to know what angle T1 is. Now, OT and SO are radii. I'm just going to do this over here, which means that T1, angle T1 is equal to angle TSO. TSO, angles opposite equal sides. And because we know that this angle at O2 is 2x, we can get that T1 is equal to TSO by saying 180 minus 2x divided by 2, which is 90 minus x, because of sum of angles in triangle. And this is now the bad boy we're going to put down here. So sine 90 minus x. Immediately your brain should be thinking co-ratio. Ding, ding, ding. If not, it's now thinking co-ratio. Right, so now we're going to isolate ST because that's what we want. So ST is equal to SO times sine 2x all over sine 90 minus gives me cos x. Now, I don't want a cos. In what I'm trying to prove, I don't want cos. But I know that my sine double angle expands to sine x cos x. And so when I now divide everything by cos x, the coses are gone. ST is equal to 2 SO sine x. Nice and easy. All right. So when you get questions like this, and what I want you to kind of get in your heads is that, yes, this is a problem-solving question. Yes, this is a harder question. But problem-solving questions are based on knowledge that you have. I'm never going to ask you to, like, integrate. You don't know what integration is. Some of you might, but you don't know what that is. I'm not going to ask you to use a matrix to go and solve that. You don't know what that is. Problem solving is based on knowledge that you have. All right. So the second I'm seeing sine, trig. When I identify the two sides, ST and SO, triangle. So think sine rule, cos rule. The fact that I only want sine x kind of in my head says go with the sine rule. If you want sine, go with the sine rule. Yes, I ended up having a cos there. Not an ideal situation, but because of the double angle, I was able to deal with it. Like I say, you can go do cos rule with this. I personally, I don't know why I chose a cos rule initially, actually. I went cos rule initially. I feel like it was just more work than it was worth. Personal opinion. But everything that we just did here was a 2D trig question. This was like me saying in 2D trig, here's the triangle STO where O2 is equal to 2x. Prove that ST is equal to this. It's a 2D trig question. So that's grade 10. Grade 10, grade 11, shame. Poor grade 10s. Grade 11 question. It just is unfamiliar because of the context in which it's presented to you within Euclidean geometry. All right, so when you get questions like this, don't think you can't do it. Think about, what do I have? Where is it in my diagram? What knowledge do I actually possess in order to answer this? Because I'm going to assume, you can tell me if I'm wrong. Now that I've done it, you're probably thinking, oh, that's so easy. Or it was a lot easier than I thought it was when I first read the question. All right. So I absolutely can. So the 90 minus x I got from sum of angles in a triangle. So if you have a look at your triangle, I'm such a nana bean sometimes. Right, so our triangle. So this pink triangle over here. No O2. So O2 we know is equal to 2x. And because OS and OT are both radii, it means that this angle T1 and this angle over here, what is this? TSO, they are equal to each other. So that's what I'm saying here. T1 is equal to TSO because of angles opposite equal sides. Then to get the 90 minus situation, I would say 180 minus the angle I have 2x. And then because those angles are both the same, I would divide whatever that is by 2. 180 divided by 2 is 90. 2x divided by 2 is x. So 90 minus x is the size of each of those angles. Does that make sense? Right, if it doesn't make sense, just let me know. I'm just going to do this for you guys to take screenshots. I have just rewritten 9.3. Okay, so just let me know if that all made sense. If not, just let me know. And then, guys, it is 7 o'clock. Obviously, we haven't done the similarity proportion. We will do that on Wednesday, obviously. Please keep asking me questions. Lelo, I'm going to figure out that question. I feel like I know what I'm doing wrong. I just need to go back and have a look, and then I'll put an answer on the Google Classroom as soon as I have one, or I will, if you want to wait until Wednesday, I can do it on Wednesday as well.